Today we're doing section 3.5, which is exponential growth and decay word problems, and this is the first day in this section. So first thing I want to discuss is the exponential growth and decay model. Just to kind of recall, our compounded continuous formula looks something like this. So the exponential growth and decay model looks very similar, except there's a few variables that have changed, but the overall placement of the equation is the same. So essentially, we're going to be kind of talking about like an object and how much it grows over time. So your A naught would be like your initial, or original amount. Your K is your growth rate. And typically we don't know the growth rate. That's what we have to solve for first. And then your big A would be like your ending value. So very similar kind of setup. It's just the variables kind of mean different things. So for our first example, this is the graph in figure 3.22 shows the U.S. population in millions for 5 selected years from 1970 through 2007. In 1970, the population was 2,003.3 million. By 2007, it had grown to 300.9 million. Find an exponential growth function that models the data from 1970 through 2007. So for letter A, again, we're going to use this information to create our equation. So I know my ending value is the 300.9. I know my starting value is 203.3. E is part of the equation. I don't know the growth rate, that's K. And what I do know is the time. So from 1970 to 2007, a total of 37 years has elapsed. So now the goal is that we can solve for K so that we can write an equation. So this is kind of like the idea of direct variation or inverse variation, where you have to find K first so you can find the second part. So the first thing that we would do is divide by 203.3. And again, you can leave that as a fraction or you could put it as a decimal. So we get 1.48 when we divide it, equals e to the 37k. And in order to solve something like this, we need to put it in log form. So we're going to use natural log because the base is e. So I have ln base e of 1.48 equals 37k. And then we would divide both sides by 37. So again, you would find what natural log of 1.48 is, divide that by 37. And we get K is equal to 0.011. So we'll, again, use 3 decimal places for our K value. So now to kind of write our general equation, I would say the general equation is A equals 203.3 e to the 0.011 t. So notice I left t as a variable and I left big A as a variable, so now we can find any information they ask. So notice in letter B, it says what is the population, or by what year will the population be 315 million. So now for letter B, I have 315 equals 203.3 e to the 0.011 t. And you're going to notice that the way we solve is almost identical, the process. So again, we would divide by this 203.3. So we get 1.55 equals e to the 0.011 t. And now we put it in natural log form. So I have ln e of 1.55 equals 0.011 t. And then we divide both sides by 0.011. And after we type all this in the calculator, we get t equals approximately 40. So that means it'll take about 40 years. So 40 years from 1970 would be 2010. So by 2010, the population would reach 315 million. Our next example involves exponential decay, and it's used in determining the age of fossils and artifacts. The method is based on considering the percentage of carbon-14 remaining in the fossil or artifact. Carbon-14 decays exponentially with a half-life of approximately 5,715 years. The half-life of the substance is the time required for half of the given sample to disintegrate. Thus, after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Carbon dating is useful for artifacts or fossils up to 80,000 years old. Older objects do not have enough carbon-14 left to determine the age accurately. So use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. So we're going to kind of go about this and assume that if my original amount was 1, then the ending value would be a half. So we're going to say a half, and then the original amount was 1. E, I don't know what K is, and I know T is 5,715. Now, obviously, if I divided both sides by 1, nothing's going to change. It's still going to be equal to a half. So I don't really need that 1 there. When I divide both sides by 1, it would just go away. And now to solve like this, we would put it in natural log form. This is letter A, by the way. So ln of E of 1/2 equals 5,715K. And then we know we would divide both sides by 500,715 on both sides. So when I do this, we get K is equal to a negative 0.000121. And a way to kind of check your K value is you need to ask yourself, is this exponential growth or decay? So because this one's decay, my K value is negative. In the last example, we had growth. The population was growing. That's why K was positive. So now to use our general equation that we can use for any given value, we would say A equals 1e to the negative 0.000121 t. So now we can use this information to solve for letter B. So letter B says in 1947, earthy and ware jars containing what are known as the Dead Sea Scrolls were found by Arab Bedouin herdsmen. Analysis indicated that the scroll wrapping contained 76% of the original carbon-14. Estimate the amount of the Dead Sea Scrolls. So I'm going to flip to the next screen so I have more room to solve. So 76% is going to be like our ending value. This we do have to write as a decimal. So my ending value would be 0.76 equals 1e to the negative 0.000121t. And again, when I divide both sides by that 1, the 0.76 is going to remain the same, so I can kind of take that 1 away. And now I'm at the point where I put it in natural log form. So I have ln e of a 0.76, and this is equal to our K value times our T. And again, to get T by itself, I would divide by that big long decimal. So when I type this in the calculator, we'd have ln 0.76, close parenthesis, divide by negative 0.000121. And when we do that, we get approximately 2,268 years. So the objects that they found were about 2,268 years old plus the number of years between 1947 and the current year. So we're going to pick up and do some more practice on these types of problems tomorrow.